Now, one of the most important optical instruments is the eye. In the eye, what you have is some material that is photosensitive, that's the retina. Right? When the photons hit the retina, if they produce changes in the retina, electrochemical signals that travel all the way to the brain. So you have, this is pretty much a camera. It's exactly like a camera. You have some photosensitive material on the back. You have an aperture here through which the light can come in. If you didn't have a lens, you would have to have a very, very small opening to make sure that one-to-one correspondence between the light coming from one point on the object and the place where that light ray hits the photosensitive material, right? So if you had a very small pupil, then you wouldn't need a lens, right? The problem with that is that the pupil will be so small that the image is not very bright. The image of the object is very, very dim. And so it's past the point where it would be feasible. So the answer for the eye, which nature found millions and millions of years ago, and that humans found more recently, is that you can open up a much bigger pinhole, okay? And the sorting job, the element that makes sure that only one point of the object corresponds to one point on the screen, it's going to be a lens. In the eye, you have actually two important places where the bending of light rays happens. The first one and the most important one is the cornea. That's where 80% of the bending of the light rays occurs. And that's because the cornea, which has an index of refraction of 1.376, the transition is from the light rays are going from air, crossing into cornea, and that's a big difference in index of refraction. So that produces strong bending of light rays. From Snell's law, you can see that, right? But inside here, once the light rays have gone through the cornea, there's not a lot of things happening here. There is things happening, bending of light rays, but it's not very strong just because of the numbers. Look at the numbers. The index of refraction in this part is 1.336. The index of refraction inside this lens, the crystalline lens, varies between 1.38 and 1.4, which is pretty close to this. And then in here is pretty much the same as this one again. So there's not very strong bending of light rays happening already inside the eye. The main thing happened here on the cornea. And if the shape of your cornea is changed by a little bit, then you don't see images clearly. So that's the idea. So you do have a lens here, and the importance of that lens is the next thing that I'm going to talk, which is accommodation. But so this lens is able to change its shape. There is muscles that are attached to it, and those muscles can make the lens, they can squeeze it and make it bulge out, or they can relax and the lens would have the normal shape, the relaxed shape of it. When a lens changes shape like this, when the radius of curvature of the lens changes, the focal length of that lens changes also. And I'll show you in a minute why that's important. But the basic idea with here, of course, is that if you have light rays coming from, say, a very far away object, coming in parallel, when the ciliary muscles are relaxed, the light coming in parallel gets focused on the retina, right on the retina. So that produces a sharp image of an object that is infinitely away. Okay, so looking at the stars at night, when you do that, your ciliary muscles are completely relaxed. So looking at faraway mountains and so on has a calming effect. Maybe it's because of that. Your eyes are not, those muscles are not engaged. There's no tension in your eyes. Light just gets focused right where it should be. Okay, so let's look at the issue of accommodation. So this is illustration 35.1, which you can find in Allspace. Fislets. So what I have here, what I'm trying to show here is these two lines are going to be the retina. They didn't have a solid line for that. So this line, I'm not going to move that. That's the location of the retina. And this is the lens. All the focusing power of the lens, we're going to put it in just one place, and that is this converging lens. So if you have an object that is far away, like this one, I cannot go to infinity here. so the light rays are not coming in parallel, but just assume that it's really far away, the image of the object is going to be formed very close to the focal point of the lens. If I click on the lens, it will show me the 2 points. It's 2 points that is showing. Those are the focal points of this lens. One here and one here. So when the object is far away, the image forms very close to the focal point of the lens, right? If that was true at infinity, it would be right at the focal point. So when the eye is relaxed, when the crystalline is relaxed, then the focal point of the eye is right on the retina. Okay? Now what happens when now you focus on an object that is not at infinity but closer? The image of that object has been, as I moved it all the way to here, it moved back from, it was originally here, a little ahead of this, and now it moved here. And if I keep moving it, it just keeps moving away. Until it moves to infinity, right? Which is at the point where the object is now at the focal point of the lens. Then the light rays are not going to converge anywhere. Okay? So as you move it from infinity closer and closer, notice that the image is being formed behind the retina. It keeps moving back. Okay? That's not good, of course, because the image needs to be formed on the retina or it won't be sharp. It will be very blurry. So what the eye does is it has to, well, what a camera would do, let's talk about that first. What a camera would do would be to change the location of the lens to make sure that the image is now focused back on the retina where it should be, to be sharp. So that's what a camera does. The lens of the camera comes out and comes in to allow for the image to be always focused on the CCD element of the camera or the film of the camera. But in the eye we don't do that. The eye doesn't change the location of the lens. What it does is it changes the focal length of the crystalline lens. By squeezing it with those muscles that I just talked about, you change the focal length of this lens. So the idea then would be that when the object moves closer, what the eye would do is squeeze the crystalline lens and reduce its focal length so that you bring the image back on the retina. Focus on the retina. And that happens very quickly. You don't notice that, but that's happening constantly. Every time you look at objects that are at different distances, there is an adjustment that has to happen there. And the closer you put this object, the more you have to squeeze the crystalline lens to reduce its focal length and have the image right on the retina again. Okay? The lens maker equation, which you read in your book, and there is a derivation of where this is coming from, which is just refraction and Snell's law. I won't go through that, but I want you to be aware of this equation, which tells you that when you have a lens, or to build a lens with a specific focal length, what you do is you cut these surfaces in circles. We've talked about that before. If this surface has a radius 1, and this other surface has a radius 2, and the index of refraction, say, of the outside is air, typically air, so that will be 1, and the index of refraction inside of the material that you're using is n, then this equation tells you what will be the focal length of that lens. Okay? If you apply this equation to the crystalline lens of your eye, you will notice that, well, assume that it's symmetrical, so these two R's are equal, but because the surfaces are curving in different directions, one of them is going to be a minus, and the other one's a plus. So this equation is going to turn into, details are not important, I just want to give you the idea. This equation is going to turn into something like this. R divided by 2 times n minus 1. It won't be 1 because it's not coming from air, so it will be like the n of the crystalline length minus the n of the forgetting the name of it. So that is the equation that I want to show you, because this equation tells you that if the radius of the crystalline lens decreases, so when you squeeze it, the radius decreases. When it's relaxed, then it, and the radius of curvature of a surface that is flat is very large number, right? But when the surface when the crystalline lens gets squeezed this way, the radius of curvature now becomes small. So by squeezing, you reduce the R, which reduces the focal length of the crystalline lens. Okay? So engaging the muscles does this job, which is to reduce the focal length of this lens. Okay? So when the image is formed way behind or too much behind the retina, then what you can do, what your eyes do automatically, is reduce the focal length of the crystalline lens and bring the image back on focus. There's a problem with that, which is there is a limit. You cannot do that indefinitely. You cannot compress and compress and compress the crystalline lens to give it a radius of 0. There's going to be some physical limitations on how much you can compress it. So that means there's going to be a limit to how close an object can be so that you can still accommodate and have it focus on the retina. There's going to be a limit to that, right? The limit, normally in a normal eye, the limit is not how far it can be, okay? Because focusing an object that is far away is accomplished just by the shape of the crystalline and the eye. They do the job, that does the job of producing a sharp image of an object at infinity on the retina. That's the easy job. It doesn't require any effort for you to look, if you have normal eyes, or correct it, to look at a faraway mountain. Okay? But the hard job is when the object gets pretty close to you, because those light rays are diverging so strongly from the object that when they hit the converging element of the eye, it might not be enough to bring them into convergence on the retina. It might not be powerful enough. So it turns out that because of that, normal eyes have a range of distances at which you can focus, which is from infinity all the way to 25, more or less 25 centimeters. More than that, the crystalline lens cannot accommodate anymore. All right? And then things look blurry. When you, for example, place your hand at a distance, say 10 centimeters from my hand, I cannot see that. Right?